There is a fact that has been quietly settled in laboratories, in rooms where single atoms are held still in traps of light and patient instruments record their behavior. And the fact is this: a quantum system that is watched closely enough cannot change. To look at it often enough and steadily enough is to hold it in place. Not by touching it in any ordinary way, not by reaching out a hand, but simply by asking of it again and again the question, "What are you doing now?" Ask that question often enough, and the answer becomes nothing, still nothing, the same as a moment ago. The thing that was about to move does not move. The atom that was about to slip from one state into another remains where it was. Watching in this strange corner of the world appears to act like a kind of pressure, a soft and invisible weight that keeps the future from arriving. This is not a metaphor. It is a measured effect, given a name many decades ago, demonstrated with trapped ions and cold atoms and faint pulses of laser light. And it sits at the edge of one of the deepest and least settled questions in all of physics, a question that has occupied some of the most careful minds of the last 100 years and remains, even now, without an agreed answer. The question is simple to ask and very hard to hold. What does it mean to observe something? And could observation itself, the plain act of finding out, be more than a passive glance? Could it be, in some sense we do not yet fully understand, a force? Tonight, there is no need to decide. There is only the slow turning of the question itself, examined gently, in the dark, the way one might turn a smooth stone in the hand without any hurry to set it down. Begin with the ordinary world, the world of daylight and solid things, where observation is the most innocent act imaginable. A person stands at a window and looks out at a field. The look changes nothing. The grass bends in the wind whether or not anyone watches it. The far hills hold their shape. Light leaves the sun, crosses the long emptiness, strikes the leaves and the stones and the slow water, and some small part of it scatters back and enters the eye. And from that scattered remnant, the mind builds a picture. The field does not feel the gaze. It does not stir or flinch or settle into one arrangement because a watcher has arrived. In the world we move through, to observe is to receive. The observer is a guest who takes nothing and leaves no mark. This is the meaning of observation that everyone carries without thinking. It is woven into the way people speak. To witness, to notice, to behold. All of these words describe a one-way flow, the world pouring its light outward and the watcher quietly catching what spills toward them. Even the careful measurements of classical science, the kind that built bridges and charted planets and timed the swing of pendulums, follow this gentle rule. A thermometer, lowered into a pot of water, does take a little warmth from the water in order to register its temperature. A scale weighing an object presses up against it. There is always some small exchange. But the exchange is so faint, so easily accounted for, that for most of history it could be ignored entirely. The astronomer who measured the position of a star did not move the star. The light had already left it, thousands of years before, and arrived carrying its message without asking anything in return. And so, for a very long time, the act of observing was understood to be outside the things observed. The universe was imagined as a vast machine, turning according to fixed laws, indifferent to whether anyone was present to see it turn. A falling stone fell the same in an empty wood as in a crowded square. The moon traced its path across the night, whether or not a single eye was lifted toward it. There was the world, complete in itself, and there were the watchers, latecomers who arrived to admire what was already finished. Reality first, and observation afterward, a record kept of events that had already decided themselves. Then, in the early years of the 20th century, a crack appeared in this comfortable picture. It opened slowly, in the study of the smallest things, the particles of light and matter that make up everything else. And what came through the crack has never been fully understood, only described, very precisely, and argued over ever since. To see where the trouble begins, it helps to follow light and matter down to their finest grain, to the level where a thing is no longer a smooth, continuous substance, but a countable quantity. A single photon of light, a single electron. At this scale, the rules change. They do not change a little. They change at the root, in a way that overturns the quiet certainty of the field and the window. The clearest place to meet this strangeness is an experiment so simple that it can be described in a few sentences, and so puzzling that physicists have returned to it for more than 2 centuries. It is called the double slit experiment, and its origins go back to the year 1801, when an English scholar named Thomas Young set out to learn whether light was a wave or a stream of tiny particles. He let light pass through 2 narrow openings, 2 slits cut close together in a barrier, and he watched what fell on a screen beyond. If light were simply a hail of little grains, he expected 2 bright bands, one behind each slit, where the grains piled up. Instead, he found something else. He found a row of many bright stripes separated by dark ones, a pattern of light and shadow spreading across the screen in regular bands. That pattern is the signature of a wave. When a wave passes through 2 openings, it spreads outward from each, and the 2 spreading waves overlap. Where 2 crests meet, they add together, and the light is bright. Where a crest meets a trough, they cancel, and the light is dark. The striped pattern is called interference, and it told Young, correctly, that light behaves as a wave rippling outward and folding through itself. The way ripples cross on the surface of a still pond when 2 stones are dropped near each other. For a century, this seemed to settle the matter. Light was a wave. The argument was over, but it was not over. In the new physics of the 20th century, light revealed a second face. It could also arrive in discrete pieces, indivisible packets of energy, each one a single photon. And matter, which everyone had always taken to be made of solid particles, revealed a wave face of its own. An electron, fired alone across an empty chamber, would also fan out and fold through itself, and lay down the striped interference pattern, as though it too were a wave. This was the discovery that broke the old picture. The particle and the wave, which the ordinary mind keeps in separate drawers, turned out to be 2 aspects of a single underlying thing, and which face it showed depended, somehow, on how it was met. Here is where the strangeness deepens, and where observation first steps onto the stage as something more than a witness. Consider the double slit performed not with a bright beam, but with single particles, 1 electron at a time, released so far apart that no 2 are ever in the chamber together. Each electron leaves its source alone, crosses the gap, passes the barrier with its 2 slits, and strikes the far screen, leaving a single small mark where it lands. 1 electron, 1 point of arrival. There is nothing wave-like about a single dot. And yet, as the dots accumulate, hundreds of them, thousands, tens of thousands, gathering one by one over hours, the pattern that slowly emerges from the scatter of points is the striped pattern of interference. Each electron arrives as a particle, a single dot, but the whole population arranges itself as a wave. Each lone electron, it seems, must somehow pass through both slits at once and interfere with itself, spreading out as a wave of possibility on its way across the gap, before collapsing back into a single point at the moment of arrival. This is the thing called superposition, and it deserves to be set down gently, because everything that follows rests upon it. A quantum system, left to itself and unobserved, does not occupy a single definite state. It occupies, in a sense, that the mathematics makes exact, even though words struggle to hold it, all of its possible states at once, blended together, each carrying a certain weight. The electron does not go through the left slit. It does not go through the right slit. It goes through both, as a spread-out wave of possibility, and only when it strikes the screen and leaves its mark does it become, suddenly and definitely, an electron that arrived in one particular place. The superposition is not a statement about our ignorance. It is not that the electron really went one way and we simply failed to notice. The interference pattern itself is the proof. A pattern that requires both paths to be taken cannot arise from a particle that quietly chose only one. The bothness is real, written into the striped light on the screen. Now the experiment turns, and observation enters. Suppose a careful watcher wishes to know which slit each electron truly passes through. Suppose a small detector is placed at the slits, a device that registers the passage of an electron through the left opening or the right. The watcher now possesses, for each electron, a definite answer. This one went left, that one went right, and the moment that knowledge becomes available, the striped pattern on the far screen vanishes. In its place appear two plain bands, two simple heaps of dots behind the two slits, exactly the pattern one would expect from ordinary little grains that each took a single path. The wave is gone. The interference is gone. By learning which way the electron went, the watcher has changed what the electron does. Read that again slowly, for it is the hinge of the whole matter. Nothing has been done to the electrons except to find out about them. The slits are unchanged. The screen is unchanged. The only difference between the world of stripes and the world of two plain bands is whether the path was known. Knowledge alone, the mere availability of an answer, has reached back into the experiment and altered its outcome. The act of observing has done something that the absence of observing did not do. It is from moments like this that the strange suspicion grows. The suspicion that observation in the quantum world is not the gentle one-way flow it is in the world of fields and windows, but something active, something that participates, something that presses upon reality and helps to settle what reality will be. And it is here that the words must be chosen with great care, because this is exactly the place where wonder can slide into error, where a true and astonishing fact can be dressed up in claims it cannot support. So the rest of this long night will move slowly, and will try, at every step, to keep clear the line between what has been measured and shown, and what remains a matter of interpretation and honest disagreement among the people who have studied it most. The first thing to make clear is what the word observer means here, because it carries a great deal of unearned weight in the way these ideas are often told. In popular tellings, the observer is a person, a conscious mind, a watcher whose awareness somehow reaches into the atom and shapes it. This is a misunderstanding, and it has caused more confusion than almost any other single idea in the public life of quantum physics. In the experiment just described, no human awareness is required. The detector at the slits does the observing. It is an arrangement of matter, a piece of apparatus, and it would register the electron's path, whether or not any person was in the building, whether or not anyone ever looked at its record, whether or not the record was simply written to a disk and forgotten. What matters is not that a mind became aware. What matters is that the electron interacted with something. That information about its path became fixed in the wider world, entangled with the state of the detector, and through the detector with everything the detector touches. This is the quieter and more accurate meaning of observation in physics. To observe a quantum system is to interact with it in a way that leaves a trace, that couples its private wave-like spread of possibilities to the larger fabric of things, to instruments and air and warmth and light, until the spread can no longer fold back through itself and show its wave face. The observer need not be alive. The observer need not be aware. The observer, in the end, may be nothing more than the rest of the universe, doing what it always does, exchanging photons and jostling atoms, and refusing to leave anything truly alone. When the path of the electron becomes a fact written somewhere in the world, even a fact no one will ever read, the stripes disappear. It is the becoming a fact that matters, not the being known by a mind. And yet the interaction is real, and it does press upon the system. This is the part that is true, and it is worth holding onto even as the mind discards the false part about consciousness. To find out which slit the electron took, something must touch the electron. A photon must scatter from it, or a field must respond to it, and that touch carries energy and direction, and it disturbs the very thing it reports on. In the world of fields and windows, the light that lets us see the grass takes nothing the grass will miss. In the world of single electrons, the light that lets us see the electron is comparable in size to the electron itself, and the seeing is a collision. You cannot look at so small a thing without striking it. The glance is a touch, and the touch leaves a mark. This was the insight that the young German physicist Werner Heisenberg reached for in the year 1927, when he tried to imagine the gentlest possible measurement of a particle's position. To locate a thing, he reasoned, you must illuminate it, and to locate it sharply, you must use light of a short wavelength. And light of a short wavelength carries a hard kick of momentum, so that the very act of pinning down where the particle is sends it lurching off with a velocity you can no longer know. Look closely at where it is, and you blur how it moves. Look closely at how it moves, and you blur where it is. He drew from this a principle, the uncertainty principle, which states that certain pairs of properties, such as position and momentum, can never both be known with perfect sharpness at the same time. The more precisely one is fixed, the more the other dissolves into a haze. It would be tempting to take the uncertainty principle as the whole story, to say that observation disturbs, and the disturbance explains the blur, and there the mystery ends. But the truth is deeper and stranger than that, and honesty requires saying so. The image of the clumsy collision, the light kicking the particle, is a useful picture, but it is not the heart of the matter. The uncertainty is not merely a limit on our knowledge caused by our clumsy instruments. It is a property of the thing itself. The electron, before any measurement, does not secretly possess a sharp position and a sharp velocity that our looking spoils. It does not have them to spoil. Its position and its motion are themselves spread out, blended, held in the same wave-like fog of possibility as its passage through the two slits. The uncertainty principle describes not the failure of our seeing, but the fundamental texture of what is there to be seen. a texture in which sharp answers do not exist until they are demanded, and demanding one answer washes out the other. The disturbance is real, but underneath the disturbance lies something more basic, a world that simply does not keep all its values fixed and waiting in the dark. Here, the central puzzle finally shows its full shape, the puzzle that physicists call the measurement problem, and around which all the rest of this night will turn. It can be stated with great precision, and the precision is part of why it has refused to go away. Quantum mechanics, the theory that describes all of this, has at its core a single rule for how an undisturbed system changes over time. The rule is written in an equation discovered by the Austrian physicist Erwin Schrödinger in the year 1926. The equation is smooth, exact, and entirely predictable. Given the wave-like state of a system at one moment, it tells you, without any gap or guesswork, exactly what that state will be at every later moment. It is as orderly as the swing of a pendulum, and crucially, it preserves superposition. Feed it an electron spread across two slits, and it gives you back an electron spread across two slits, evolving, folding, but never choosing. Under this equation, nothing ever becomes definite. The wave of possibility flows on forever, smooth and undecided. If the Schrödinger equation were the whole of physics, the world would never settle into single facts. It would remain a blur of every possibility at once, all the way up from the electron to the screen, to the detector, to the laboratory, to the watcher. But that is not what happens. When the electron strikes the screen, it makes one mark in one place. When the detector checks the slit, it gives one answer, left or right, not both. Somewhere between the smooth flowing superposition and the single definite fact, the manyness collapses into oneness. The wave of possibility, spread across all its options, becomes a single outcome, and the others vanish as though they had never been weighed at all. This sudden settling has a name. It is called the collapse of the wave function, the moment when a spread of possibilities becomes a single actuality. And here is the wound at the center of the theory. The Schrödinger equation, the one rule for how things change, does not describe this collapse. It cannot. It only ever preserves the superposition. The collapse is something extra, something laid on top of the equation by hand, invoked whenever a measurement occurs, to explain why we always find one world and not the smeared blur of all of them. There is one law for how quantum things evolve when no one looks, and a second, different process that takes over the instant they are looked at. And nothing in the theory says exactly when the first gives way to the second, or how, or why. This is the measurement problem. It is not a problem of insufficient data or imperfect instruments. It is a problem in the bones of the theory, a place where the most successful description of the physical world ever devised simply stops describing and starts instead to give a recipe. Use the smooth equation up until a measurement. At the measurement, set the equation aside and collapse the possibilities into one, with the chance of each outcome given by a separate rule. That separate rule, called the Born rule after the physicist Max Born, who wrote it down in the year 1926, works flawlessly. It tells you, for any quantum situation, the probability of each possible result, and these probabilities have been confirmed to staggering precision across a century of experiment. The recipe works. It always works. But a recipe is not an explanation, and the theory cannot say what a measurement is, what counts as one, or what physically happens during it. It only tells you what to do when one occurs. And so the question of observation becomes the question of measurement, and the question of measurement becomes the deepest unsolved question of the quantum world. What is it about being observed, being measured, being touched, and recorded by the wider world that turns a flowing blur of possibility into a single hard fact? Is observation a passive bookkeeping, merely noting what was already there? Or is it an active event, a real physical happening, something that reaches into the undecided and decides it? The smooth equation has no answer. The collapse is unexplained. And into that silence, that gap in the most precise theory ever built, physicists have poured a century of thought, disagreement, and wonder. Before going further into the disagreement, it is worth dwelling on the one place where observation looks most undeniably like a force, where the watching seems to reach out and hold the world in place. It is the effect described at the very beginning of this night, the watched system that cannot move, and it has a name drawn from an old paradox of motion. In the ancient world, a philosopher named Zeno of Elea proposed a set of riddles meant to show that motion itself was an illusion. One of them concerned an arrow in flight. At any single instant, Zeno argued, the arrow occupies a definite place, and in that frozen instant, it is not moving, for movement takes time and an instant has none. But if the arrow is motionless at every instant, and the whole of its flight is made of instants, then how can it ever move at all? The flight, Zeno suggested, is a sum of stillnesses, and a sum of stillnesses can only be stillness. The arrow never truly flies. It was a puzzle about how change can be built out of changeless moments, and for more than 2,000 years, it remained a curiosity of philosophy, a clever trap of words. In the year 1977, two physicists, Baidyanath Misra and George Sudarshan, gave Zeno's old riddle a new and literal life inside quantum mechanics. They asked what would happen to an unstable quantum system, a system poised to change from one state into another, if it were measured over and over again in very rapid succession. The answer they found was remarkable. The more often the system was observed, the more its change was held back. And in the limit of continuous observation, in the ideal of looking without pause, the change would be suppressed entirely. The system would be frozen in its original state, unable to evolve, pinned in place by nothing more than the relentless act of being watched. They named this the quantum Zeno effect, after the arrow that cannot fly, and it carries a folk shadow in an old kitchen saying that a watched pot never boils. The reason for it lies in the rhythm of how quantum systems change, and it is worth following slowly, because it shows how deeply observation is woven into the unfolding of events. When a quantum system begins in a definite state and is left alone, it does not leap immediately into a new state. At first, in the very earliest moments, it changes slowly, gathering its departure gradually, the possibility of the new state growing from nothing. Each measurement asks the system, in effect, which state are you in, and forces it to answer with a single definite reply. If the measurement comes very soon after the last one, while the system has barely begun to drift away from its starting state, the overwhelming likelihood is that it answers, still here, still the original, and in answering it collapses back to that original state, its small accumulated drift erased, its clock reset to zero. Then it begins to drift again, and again it is asked, and again, being barely departed, it answers still here, and again it is thrown back to the start. Measure quickly enough, and the system spends its whole existence in that earliest sliver of departure, never given the uninterrupted stretch of time it would need for the new state to fully grow. The future never accumulates. The arrow, examined at every instant, never flies. This is not a thought experiment alone. In the year 1990, a team of physicists at the National Institute of Standards and Technology, among them Wayne Itano, Daniel Heinzen, John Bollinger, and David Wineland, carried it into the laboratory. They took a small collection of charged beryllium atoms, held them in a trap, and prepared them in one energy state with the intention of driving them, with a steady radio signal, into another. Left to the signal alone, the atoms would have made the transition in the expected way, climbing from the lower state to the higher over the course of the drive. But the experimenters interrupted the climb with brief pulses of laser light, each pulse a measurement, each one asking the atoms which state they occupied. As they made these measuring pulses more and more frequent, the transition slowed. The atoms, asked again and again where they stood, increasingly answered where they had begun, and the more often they were asked, the fewer of them completed the climb. The watching held them back. The effect that Misra and Sudarshan had drawn from the equations stood revealed in the behavior of real atoms in a real trap. It must be said, in the spirit of care that this subject demands, that physicists have argued for years about exactly what the 1990 experiment showed, and about the deepest meaning of the effect. Some have questioned whether the slowing was a true collapse, the genuine resetting of the system by measurement, or whether it could be explained as an ordinary disturbance, the laser pulses simply pushing the atoms around in a way that happened to impede the climb. The mathematics of the effect is not in dispute, and frequent measurement does suppress change. But whether to call this a fundamental feature of observation or a particular kind of physical jostling remains a matter of interpretation, bound up with the larger unsolved question of what measurement is. There is also a mirror image of the effect, called the anti-Zeno effect, in which measurements timed differently can hasten a system's change rather than hinder it, speeding the very departure that frequent watching would freeze. Observation, then, is not simply a break. Depending on its rhythm, it can hold the world still or hurry it along. Either way, it does something. It is not the passive guest of the field and the window. It reaches in. And so, in the quantum Zeno effect, observation wears its most force-like face. To watch is to hold. To attend without pause is to suspend the flow of change. There is a strange tenderness in the image, an atom kept from its own future by the simple constancy of being looked at, like a held breath that cannot be released so long as someone is listening. If anywhere observation seems to press upon reality with something like a physical weight, it is here, in the frozen atom, in the arrow that will not fly while it is watched. But it would be a mistake, and an instructive one, to conclude from this that observation must always be violent, that to look is necessarily to seize and to alter. For there is another body of work, quieter and subtler, that shows the opposite. That shows how a system can be glanced at so gently that it is scarcely disturbed at all, and yet still yields up a little of its secret. This is the study of weak measurement, and it complicates the picture in a way that is worth holding alongside the frozen atom, so that neither image hardens into the whole truth. In the year 1988, three physicists, Yakir Aharonov, David Albert, and Lev Vaidman, working in the tradition of asking what can be said about a quantum system in the interval between two measurements, proposed a new and gentler kind of looking, an ordinary measurement, the kind that collapses a sewer position into a single sharp answer, is what they called a strong measurement. It extracts a complete answer, and in doing so, it destroys the delicate spread of possibilities, leaving the system in one definite state. But a measurement, they reasoned, need not be all or nothing. The coupling between the system and the measuring device could be made very faint, so faint that any single reading reveals almost nothing and disturbs the system almost not at all. The cost is that one such gentle glance tells you next to nothing, buried in noise. But repeat the gentle glance across a great many systems prepared in the same way, and average the faint results together, and a real value emerges from the haze, a property of the system extracted without ever collapsing it, a secret read without breaking the seal. These averaged results, called weak values, behave in ways that strain ordinary intuition. They can fall far outside the range of any value the property could normally take, a spin that should read either up or down, somehow averaging to a number 100 times larger than either. The meaning of these strange numbers has been argued over for decades, and there are respected physicists who hold that weak values are deeply quantum, revealing something genuine about a system caught between its past and its future, and others who hold that they are statistical artifacts, curiosities of how the averaging is done, dressed up in mysterious clothes. That argument, too, remains open. But the simpler lesson stands, and it is the one that matters here. Observation is not a single fixed thing with a single fixed weight. It is a dial that can be turned. At one extreme, it is the hard collapse, the strong measurement that seizes a full answer and freezes the atom in place. At the other extreme, it is the faintest possible touch, a watching so soft that the system flows on almost as though no one had looked at all. Between information and disturbance, there is a trade. The more you take, the more you alter. The less you take, the gentler you leave it. There is no looking that takes everything and changes nothing, and there is no looking, however gentle, that takes something for free. But the price is not fixed. It slides. This sliding scale is itself a clue, and it points away from the idea that consciousness or knowledge is the active ingredient in observation, and towards something more physical and more general. What disturbs the system is the strength of the interaction, the firmness of the coupling, the amount of information that flows out into the world. A faint coupling, a weak entanglement, leaves the sewer position nearly intact. A firm coupling, a strong entanglement, collapses it. Watching is not a mind reaching in. It is a physical linkage, a thread of correlation tied between the system and its surroundings, and the tighter the thread is drawn, the more the system is pulled into definiteness. This suggests that the real engine of collapse, if collapse is the right word at all, is not observation in the human sense, but interaction in the physical sense. The unavoidable coupling of a small thing to the vast and restless world around it. And that suggestion leads to one of the most important developments in the modern understanding of these matters. A development that does not solve the measurement problem, but reshapes it, and pushes the mystery into a smaller and sharper corner. That development is called decoherence, and to understand it is to see why the boundary between the quantum world and the ordinary world is not a wall but a slope, and why observation, in the everyday sense, almost never has to happen at all for definiteness to take hold. The idea was first pressed forward by the German physicist Heinz Dieter Zeh near the end of the 1960s, and it was developed and given much of its modern shape by the physicist Wojciech in the decades that followed. It begins from a plain and inescapable fact about the world. Nothing is ever truly alone. The lone electron crossing an empty chamber is an idealization, a convenience of the textbook. In reality, every object is bathed in a sea of other things. There are stray photons drifting through, the faint warmth of nearby surfaces, the gentle pressure of air molecules, and the dim glow of the cosmic background radiation that fills all of space. A dust mote in a sunbeam is struck by countless photons every second. A speck of matter at room temperature is in ceaseless contact with the jostling warmth around it. The environment, the rest of the world, is always present, always touching, always exchanging. Now, recall what happens when a quantum system interacts with something. Its delicate spread of possibilities, its superposition, becomes linked to the state of whatever it touches. The two become entangled, their fates woven together, so that the wave-like spread is no longer the private property of the system alone, but is shared out into the larger thing it has joined. And here is the crucial point. The wave nature of a quantum system, its ability to fold back through itself and show interference, depends on the different parts of its superposition remaining coherent, remaining in a fixed and orderly relationship with one another, like the matched ripples that cross on a pond to make a clean pattern. The interference, the stripes on the screen, requires that orderly relationship to be preserved. But when the system entangles with a vast and chaotic environment, with uncountable photons and air molecules and warmth, that orderly relationship is not destroyed so much as scattered, spread out among so many other particles, carried off in so many directions, that it can never again be gathered back. The information that would be needed to bring the parts of the superposition into interference is not gone from the universe. It is simply dispersed beyond any hope of recovery, smeared across the whole environment, leaking outward at the speed of light. This dispersal is decoherence, and it happens with astonishing speed. For anything larger than a single atom, for a dust mote, a molecule, a drop of water, the coupling to the environment is so strong and so constant that the superposition is scattered into incoherence almost instantly, in a span of time so short it can scarcely be written down, fractions of a fraction of a second beyond all imagining. This is why the everyday world looks the way it does. This is why a chair is never seen in two places at once, why the moon does not blur across its orbit, and why a person never finds themselves spread across a superposition of standing and sitting. The objects of ordinary life are far too large, far too warmly and busily entangled with everything around them, to hold a superposition for any length of time that could ever be noticed. The quantum spread of possibility is not forbidden to them in principle. It is simply scattered away faster than thought. The grass in the field does not need a watcher at the window to make it definite. The sunlight falling on it, the air moving through it, the warmth of the ground, all of these are already ceaselessly doing the watching. The environment is the observer. The universe measures itself, everywhere, all the time, without a single mind being present. In this light, the strange experiments with single electrons take on a clearer meaning. The reason a laboratory must work so hard, with such cold and such isolation and such care, to see the wave face of a particle is precisely that the wave face is so fragile, so easily scattered by the slightest contact. To keep an electron in a clean superposition long enough to lay down its stripes, the experimenters must shield it from the warm and noisy world, must hold it in a near-perfect emptiness, must keep it from being touched, and the moment they place a detector at the slits, The moment they let the electron's path couple to a piece of apparatus and through it to the environment, the superposition is scattered and the stripes are gone. The detector is not special because it is a detector. It is special because it is a doorway through which the electron's private spread of possibility escapes into the wide world and is lost. Any sufficiently firm contact would do the same. Observation, in this account, is simply the name we give to the system's entanglement with its surroundings, becoming irreversible. Decoherence also explains something subtle and beautiful about why the world has the particular shape it does, why it is built from definite locations and steady objects rather than from some other kind of arrangement. The environment, it turns out, does not scatter every kind of superposition equally. It is most aggressive toward superpositions of position, toward an object being spread across two places, because position is what photons and air molecules most readily reveal when they bounce off a thing. States that are localized, an object sitting definitely here rather than smeared across here and there, are the ones that survive the constant scattering. Jerk called these the pointer states, the states robust enough to endure the relentless monitoring of the environment, the states that get selected to persist, while all the more exotic superpositions are washed away. He called the selection process by a careful name, environment-induced superselection. And the picture it paints is one in which the classical world, the world of definite things in definite places, is not opposed to the quantum world, but emerges from it, sieved out of the boundless quantum possibilities by the ceaseless filtering action of the environment. The solid, familiar world is what remains after the universe has finished, in every instant, scattering away everything too delicate to survive its own attention. This is a profound and well-supported account, and it has become something close to the standard understanding among physicists of how the quantum gives way to the classical. It dissolves much of the old mystery. It removes the need for any conscious observer, any special role for the mind. It explains why superpositions are never seen at large scales, why the boundary between the quantum and the classical is a smooth and rapid slope rather than a sharp wall, and why the world is full of definite things. And yet, in the spirit of honesty that this subject demands above all, it must be said plainly that decoherence does not solve the measurement problem. It comes close, and it changes the shape of the problem, but it leaves the deepest part untouched, and the people who understand it best are the first to say so. Here is the part that it does not solve. Decoherence explains why we never observe a superposition. It explains why the orderly relationship between the parts of a superposition is scattered beyond recovery, so that interference can no longer appear, so that the detector never points to two results at once in any way we could detect. But scattering the interference is not the same as choosing an outcome. After decoherence has done all its work, the system together with its environment is still, by the smooth equation, in a superposition. It is a superposition that can no longer show its wave face, a superposition whose parts can no longer be brought back together, but a superposition all the same, containing all the outcomes, each with its weight. Decoherence turns a blended superposition into something that looks, for all practical purposes, like a collection of separate definite possibilities, each going its own way. But it does not, by itself, explain why only one of those possibilities becomes the single fact that is actually experienced, while the others fall silent. It explains why we do not see the blur. It does not explain why we see this particular outcome rather than that one, why there is a single definite result at all rather than the full set of them coexisting. The problem of the single outcome, the deepest splinter of the measurement problem, remains. And so, after all the genuine progress, the old question is still standing, only sharpened. The smooth equation never chooses. Decoherence hides the unchosen possibilities so thoroughly that the world looks classical and definite, but something, somewhere, still seems to select the one result that is lived, the one mark on the screen, the one answer at the slit, the one world that is found. What that something is, whether it is a real physical collapse, or an illusion born of our position inside the system, or a splitting of the world into many, is the question that divides the interpretations of quantum mechanics. These interpretations are not idle philosophy. They are serious attempts by serious people to say what is actually happening when observation turns possibility into fact. They cannot all be right. As yet, no experiment has been able to choose decisively among them. And so they coexist, like rooms in a great dim house, each offering a different answer to the same patient question, and a careful walk through them is the next part of this long night. The oldest of these rooms, and for a long time the most inhabited, took shape in the 1920s around the Danish physicist Niels Bohr and the circle of thinkers who gathered near him. And it carries the name of his city. It is called the Copenhagen interpretation, though it was never a single tidy doctrine so much as a family of attitudes. Its central move is a kind of disciplined refusal. It draws a line between the quantum system, which is described by the smooth flowing wave of possibility, and the measuring apparatus, which is described in the ordinary language of definite classical things. On one side of the line, superposition reigns and nothing is decided. On the other side, there are needles and dials and marks on screens, the plain, definite world of results. Measurement is the crossing of the line, the moment the quantum is registered by the classical. And at that crossing, the wave of possibility collapses to a single outcome, with the born rule giving the odds. In its more austere forms, the Copenhagen view declines to say what is really happening during the collapse, or what the wave of possibility even is, whether it is a real thing in the world or merely a tool for predicting the results of measurements. The wave is a calculating device. The collapse is what happens when a measurement is made, and questions about the reality beneath the measurement, about what the electron is doing when no one is finding out, are set aside as questions that cannot be answered and perhaps should not be asked. For many decades, this was enough. The recipe worked, the predictions were exact, and the philosophical discomfort could be deferred. But the discomfort never quite went away because the line itself is never specified. Where exactly does the quantum end and the classical begin? How large must a thing be, how warmly entangled with the world, before it counts as a measuring apparatus rather than a quantum system? The Copenhagen view places the collapse at the boundary between the two, but it does not say where the boundary lies, and the more one looks for it, the more it seems to dissolve. A detector is made of atoms, and atoms are quantum. The observer is made of atoms, too. If the smooth equation governs the small things, and large things are made of small things, then by what right does anyone draw a line at all? This is the unease that drove others to look for different answers, answers in which the line need not be drawn by hand. The most radical of these answers was put forward in the year 1957 by a young American physicist named Hugh Everett in his doctoral work. and it is known as the many worlds interpretation. Everett's proposal is breathtaking in its simplicity and its strangeness. He suggested taking the smooth equation at its word, all the way up, with no collapse ever added by hand. There is no special process that turns possibility into a single fact. The wave of possibility never collapses. It simply keeps flowing and keeps branching forever. When the electron strikes the screen, the part of the wave in which it landed here and the part in which it landed there both continue to exist. When the detector reads the slit, the outcome left and the outcome right both happen. And when the observer looks at the result, the observer too enters a superposition. One version of the observer seeing left and another seeing right, each of them perfectly definite within their own branch, each of them entirely unaware of the other. The single world we seem to inhabit is, in this view, one branch among uncountably many, all of them equally real, the whole of reality endlessly dividing into parallel histories with every quantum event. Nothing is ever chosen because everything happens. The appearance of a single definite outcome is just the experience of a single branch, which cannot see the others because decoherence has scattered the connections between them beyond all recovery. It is a vision that many find extravagant beyond belief, an entire universe multiplied without limit to avoid the embarrassment of a collapse. And yet, it has a severe and stubborn elegance. It needs only the one equation, the smooth one, applied without exception. It introduces no mysterious line, no special role for the observer, no unexplained process. The observer is just another physical system, entangling with the world like any other, branching like any other. In the many worlds account, observation does nothing special at all. It does not collapse anything. It merely correlates the observer with the outcome, draws them into the same branch, so that this version of them finds this result. There is no force in the looking, because there is no collapse for a force to cause. The strangeness is moved from the act of observation, where Copenhagen placed it, into the structure of reality itself, which is held to be endlessly larger than it appears. A third room takes yet another path, and it restores to the world the very thing quantum mechanics seem to take away. A definite reality that exists whether or not anyone is looking. This is the pilot wave theory, first glimpsed by the French physicist Louis de Broglie in the late 1920s, and revived and completed by the American physicist David Bohm in the year 1952. In this account, particles are always real particles, with definite positions at all times, even when unobserved. The electron does go through one slit and not the other. It always has a definite path, but alongside the particle, there is also a wave, a real physical wave that fills space and guides the particle's motion, steering it according to the shape of all the possibilities. The wave passes through both slits, even though the particle passes through only one. And the wave, folding through itself, nudges the particle so that over many trials the particles pile up into the striped interference pattern. The bothness lives in the guiding wave. The oneness lives in the particle. When a detector is placed at the slits, it disturbs the guiding wave and the pattern changes. Nothing collapses because nothing was ever in superposition in the first place. The world is definite all the way down. The price of this restored definiteness is that the guiding wave must respond instantly to distant changes, so that what happens far away can steer a particle here without delay. A feature that sits uneasily with other parts of physics, but has never been shown to allow any signal or any contradiction. In the pilot wave room, observation is once again a passive thing. It reveals a position that was always there. The mystery is moved into the strange, instantaneous reach of the guiding wave. There is a fourth room, and in it, observation is given no special power at all. Because the collapse is made into a real physical event that happens on its own, with or without any watcher. These are the objective collapse theories, and the best known of them was proposed in the year 1986 by the physicists Giancarlo Gherardi, Alberto Rimini, and Tullio Weber. They suggested that the smooth equation is not quite the whole story, that to it should be added a tiny, genuinely random tendency for any particle's spread of possibility to collapse, all by itself, to a localized state. For a single particle, this tendency is so faint that collapse would almost never happen in the age of the universe, and the particle's quantum behavior is preserved. But a large object contains an enormous number of particles, all bound together, and because they are bound, the collapse of any one of them drags all the others along with it. With so many particles, the chance that at least one collapses in any tiny interval becomes overwhelming, and so a large object collapses to definiteness constantly, ceaselessly, far too fast for any superposition to survive. In this view, the boundary between quantum and classical is not drawn by an observer or by a vague line. It is set by sheer number, by the count of particles, and it falls out automatically. Small things stay quantum because collapse rarely finds them. Large things turn classical because collapse finds them at every instant. Observation has nothing to do with it. A measuring device collapses a superposition not because it observes, but simply because it is large, full of particles, and therefore subject to constant spontaneous collapse. The mathematician and physicist Roger Penrose has explored a related idea, that the collapse might be triggered not by number alone, but by gravity, that the warping of spacetime which a massive object in two places would produce becomes unstable and forces the object to settle into one place. These theories have the rare virtue, among interpretations, of being testable in principle, for they predict tiny departures from ordinary quantum behavior that ever more delicate experiments are now searching for. So far, no such departure has been found, and the smooth equation holds, but the search continues. And it is one of the few places where the long argument about observation might one day be settled by an instrument rather than a debate. There are quieter rooms still, where the question is reframed rather than answered. One of these is the view called quantum Bayesianism, often shortened to its initials, which was developed in recent decades by physicists including Christopher Futch and Rudiger Schack. In this account, the wave of possibility is not a thing in the world at all. It is a description of a particular observer's beliefs, their best reasoned expectations about what they will find if they make a measurement. The collapse in this view is nothing physical and nothing mysterious. It is simply what happens to anyone's expectations when they learn something new. Before you open the box, you expect either outcome. After you look, you know which one occurred, and your expectations update accordingly, sharpening from many possibilities to one fact. The collapse is the updating of a mind's information, no stranger than the way a person's uncertainty about a coin toss collapses the instant they see how it landed. In this telling, observation is indeed central, but not because it reaches out and changes the world. It is central because the wave of possibility was always about the observer's knowledge in the first place. An observation is simply the gaining of that knowledge. The strangeness is moved out of the physical world and into the nature of information and expectation. A related and equally subtle room is the relational interpretation, set out by the Italian physicist Carlo Rovelli in the year 1996. It proposes that quantum states are never absolute, never properties of a system in itself, but always relative to some other system with which it has interacted. There is no view from nowhere, no single objective list of facts about the world as it stands alone. There are only facts relative to this system, or that one. An electron has a definite state relative to a detector that has measured it, but it need not have any definite state relative to a more distant system that has not yet interacted with either. Reality, in this account, is a web of relationships, of mutual measurements, with no central ledger that holds the one true state of everything at once. Observation is the establishment of a relation. When two systems interact, each becomes definite with respect to the other, and that is all that definiteness ever is. There is no grand collapse of a universal wave because there is no universal wave. There are only systems becoming real to one another, one interaction at a time. And then there is the oldest and strangest room of all, the one that the popular imagination most often mistakes for the whole house. It is the idea that consciousness itself, the awareness of a mind, is what causes the collapse, that the wave of possibility flows on, branching and undecided, until it reaches a living, conscious observer, and that the entry of the result into a mind is the event that selects a single outcome. This idea was given serious form in the middle of the 20th century, growing out of the careful work of the mathematician John von Neumann, who in the year 1932 laid out the mathematics of measurement and noted that the line between the observed and the observer could be placed anywhere along the chain from particle to apparatus to eye to brain, without changing the predictions. The physicist Eugene Wigner, for a time, took the further step of suggesting that the chain must end somewhere, that the collapse must finally happen when the result reaches a conscious mind, and that consciousness, therefore, plays a unique and active role in bringing reality into being. It is an arresting idea, and it has never fully died in the public imagination. But it must be said clearly that it is a minority view, held by very few working physicists today, and that Wigner himself moved away from it in his later years, troubled by the strange consequences, and persuaded by the rise of decoherence that no special role for the mind was needed. The trouble with the idea is severe. It would mean that before the first conscious creatures appeared, the universe remained an undecided blur, which sits poorly with everything geology and astronomy tell us about a definite ancient world that long predates any mind. It would require defining what counts as conscious, drawing a line through the animal kingdom that no one knows how to draw. And it would grant to awareness a physical power that no experiment has ever isolated or measured. The honest summary is that consciousness-causing collapse is a possibility that cannot be ruled out with absolute certainty. As little in this domain can be. But it is not where the weight of evidence or the judgment of the field now rests. It is a room most physicists have walked through and left. This, then, is the great dim house of interpretations, and what is most striking about it is that all of these rooms predict exactly the same results. Every interpretation, from the austere refusals of Copenhagen to the endless branching of many worlds, to the guiding wave of Bohm, to the spontaneous collapses of objective theories, to the relational web of Ravelli, agrees with every experiment ever performed. They differ not in what they predict, but in what they say is real, in the story they tell about what lies beneath the unfailing predictions. And so the question of whether observation is a force, whether the act of finding out reaches into the world and shapes it, does not have a single answer. It has as many answers as there are rooms. In some rooms, observation is everything, the very hinge on which reality turns. In others, it is nothing, a passive correlation that changes not the world, but only the observer's place within it. The same patient experiments, the frozen atom, the vanishing stripes, the gentle weak value, support every one of these stories at once. What they cannot yet do is tell us which story is true. The strangeness of the question grows sharper still when the observer is no longer kept safely outside the experiment, but is placed within it, made into part of the very system whose definiteness is in doubt. This is where some of the most vivid puzzles in the whole subject lie, and they reach back to the earliest days of the theory, to a thought experiment devised by Erwin Schrödinger himself in the year 1935. The same man whose smooth equation lies at the heart of it all. Schrödinger was uneasy with the way the theory treated measurement, and he constructed a scenario meant to expose the discomfort by carrying the quantum strangeness up into the world of ordinary things. He imagined a cat, sealed inside a closed box, together with a small mechanism whose action depends on a single quantum event, the decay of a radioactive atom, which is itself a quantum process governed by the spread of possibility. The atom existing in a blend of decayed and not yet decayed. If the atom decays, the mechanism releases a poison and the cat dies. If it does not, the cat lives. Now the atom, unobserved, is in a superposition of both states at once, decayed and not decayed, and the mechanism is tied to the atom, and the cat is tied to the mechanism. By the strict logic of the smooth equation, the whole arrangement, atom and mechanism and cat together, should evolve into a single great superposition, a blend in which the cat is both alive and dead at the same time, neither one nor the other, until the box is opened and the situation observed. Only upon opening, only upon the act of observation, does the superposition collapse and the cat become definitely one or the other. Schrödinger did not offer this as a real prediction. He offered it as a complaint, a way of showing that something must be wrong, or at least unfinished, in a theory that seems to permit a cat to hang suspended between life and death until a lid is lifted. The everyday mind rebels, and rightly, for no one has ever opened a box to find a cat in such a blended state. The account of decoherence, developed long after, eases much of the discomfort, for a cat is an enormous warm object in ceaseless contact with its surroundings, and any superposition of so large a thing would be scattered into definiteness in a span of time too small to measure. Long before any box was ever opened, the cat becomes definite almost instantly, observed by the air around it and the warmth of its own body, with no need for a human watcher at all. But the cat still serves its purpose, for it dramatizes the unresolved core. The smooth equation, taken literally, spreads superposition upward without limit, from atom to mechanism to cat to the one who opens the box, and somewhere that spreading must stop, and a single fact must crystallize. Where, how, and why is the measurement problem wearing fur? The binding together of atom and mechanism, and cat in that scenario, is itself one of the deepest features of the quantum world, and it deserves its own quiet word, for it is the very thread by which observation does its work. When two quantum systems interact, their fates can become woven together so completely that neither has a definite state of its own any longer, and only the pair, taken as a whole, can be described. This weaving is called entanglement, and Einstein, who distrusted it, called it a spooky action at a distance, for it means that two particles, once entangled and then carried far apart, remain linked, so that a measurement of one is matched, instantly, by a corresponding definiteness in the other, however great the distance between them. No signal passes between them, and nothing can be sent this way, for the outcomes are random and reveal their correlation only when the two records are later brought together and compared. But the link is real, confirmed in experiment after experiment of ever-increasing care, and it lies beneath everything this night has described. To observe a system is, in the end, to become entangled with it, to weave one's own state together with its state, so that one becomes definite in relation to the other. Observation is entanglement made personal. The watcher and the watched, in the act of measurement, become a single woven thing. And this raises a question that the physicist Eugene Wigner pressed in a famous puzzle of his own, a question that has only grown more pointed with time. If the act of observation is itself a physical process, an entanglement, then what happens when one observer watches another observer making a measurement? Wigner imagined a friend inside a sealed laboratory, performing a quantum measurement, obtaining a definite result, while Wigner himself waited outside, unable to see in. From the friend's point of view, the measurement is complete, the outcome is settled, and a single fact has come into being. But from Wigner's point of view, standing outside, the entire laboratory, friend included, is one large quantum system that he has not yet observed. And by the smooth equation, it should be in a superposition, the friend entangled with both outcomes at once. The result not yet definite until Wigner himself opens the door. So is there a fact of the matter inside that room before Wigner looks? The friend says yes, plainly. I saw the result. Wigner's equation says not yet. Two observers, two accounts, and no obvious way to say which is right. In recent years, physicists have sharpened this old puzzle into precise theorems, and even into delicate experiments with stand-in observers built from particles of light. And some of these results suggest something genuinely unsettling, that under certain assumptions, different observers can be driven to conclusions that cannot all be made to agree, that the facts established by observation may not be absolute and shared, but may depend, in some irreducible way, on who is doing the observing and from where. The matter is far from settled, and the experiments so far involve only the simplest stand-in observers rather than conscious friends. But the direction of the puzzle is clear enough. The act of observation, which the ordinary mind takes to deliver a single public fact available to all, may be a more private and more relative thing than anyone expected. A settling that holds within one frame of reference, and not necessarily across all of them at once. Among all those who turned this question over, few held it longer or more boldly than the American physicist John Archibald Wheeler, who spent the latter part of a long life pressing on the role of the observer, with a daring that unsettled even his admirers. Wheeler had worked at the heart of 20th century physics, on gravitation and on the structure of matter, and he came to the question of observation not as a mystic, but as a hard-minded theorist who simply followed the strangeness where it led, and it led him to a proposal that took the vanishing stripes of the double slit and stretched them across the whole of space and time. Wheeler asked what would happen if the decision of how to observe a particle were delayed until the very last instant, until after the particle had already, by ordinary reckoning, committed itself to being a wave or a particle. In the double slit, the choice is usually made in advance. Either there is a detector at the slits, in which case the path is known and the stripes are absent, or there is no detector, in which case the path is unknown and the stripes appear. But suppose the choice of whether to look for the path were not made until the particle had already passed the slits and was nearly at the screen. Suppose the apparatus could be switched at the last possible moment between a setup that reveals the path and a setup that allows the interference. After the particle was already on its way, quantum mechanics makes a clear prediction. The outcome will match the final choice, the one made at the end, not any decision the particle might seem to have made earlier at the slits. If, at the last instant, the experimenter chooses to look for the path, the particle behaves as though it took a single path all along. If, at the last instant, the experimenter chooses to allow interference, the particle behaves as though it traveled as a wave through both slits all along. The choice made now appears to reach back and settle what the particle was doing then. This is the delayed choice experiment, and Wheeler proposed it in the late 1970s, and in the years since it has been carried out in the laboratory, with light and with careful timing, and the results are exactly as quantum mechanics predicts. The behavior matches the late choice, and from this Wheeler drew a phrase that has echoed ever since. No elementary phenomenon, he wrote, is a phenomenon until it is registered, an observed phenomenon. Until the question is asked and the answer recorded, there is no fact of the matter about which path was taken. The past, at this fine grain, is not a finished thing waiting to be discovered. It is, in some unsettling sense, not yet fully real until the present act of observation calls it into being. It is essential, here above all, to hold the wonder and the caution together, because this is the precise place where a true and remarkable result is most often inflated into a falsehood. The delayed choice experiment does not allow anyone to change the past in any ordinary sense. No message can be sent backward in time. No event that has already had consequences can be undone. There is no signal, no influence that a person could use to alter what has already happened to them or to anyone else. The particle leaves no usable record of a path until the experiment is complete, and so there is no settled past being overwritten, only a past that was never fully settled to begin with. The careful way to say it is that for these isolated quantum phenomena, the assignment of a definite history is itself something that depends on the whole experiment, including its final measurement, and not something fixed in advance and then revised. It is consistent with the deepest principles of physics, and it permits no paradox, no time travel, no rewriting of done deeds. What it shows is subtler and quieter than the headlines suggest, and stranger for being true. It shows that the line between past and present, between what has happened and what is being decided, is not as firm at the quantum scale as the ordinary mind assumes. Wheeler did not stop at the laboratory. He carried the delayed choice to the largest stage imaginable. Light that has traveled across the universe for billions of years, he observed, can reach us by more than one path. A massive galaxy, sitting between Earth and some far brilliant beacon, bends the light that passes it with its gravity, so that a single distant source can appear in the sky as two images, its light having traveled around the intervening mass on either side. This bending of light by gravity is real and well observed, a consequence of the way mass curves the space around it, and the doubled images of distant beacons have been seen through telescopes. Wheeler imagined using such a doubled path as a cosmic double slit. The light from a far quasar, one of the blazing cores of ancient galaxies, would have set out on its journey long before the Earth existed, long before the Sun, traveling for the better part of the age of the universe, along two paths bent around an intervening galaxy. And only now, only at the very end of that immense journey, would an astronomer choose how to combine the two paths, whether to look for which route the light took, or to let the two routes interfere. By the same logic as the laboratory experiment, the choice made now, after the light has traveled for billions of years, would appear to settle how that light behaved across the whole of its long crossing. The present observation reaches back, not across the laboratory bench, but across the depth of cosmic time. The cosmic version is enormously difficult to actually perform, for the light of a quasar would need to keep its delicate coherence across billions of years and the vast warp of an entire galaxy. And that is a fragility almost beyond reach. But as a thought, it is staggering, and it carries Wheeler's deeper conviction. He came to believe that the universe might be, in his words, participatory, that observers are not incidental latecomers to a finished cosmos, but somehow woven into the very process by which the cosmos becomes definite. He spoke of a self-excited circuit, a universe that brings itself into being through the observations made within it. The present moment of looking reaching back to help fix the past that produced the looker. He summarized his late thinking in a compressed slogan, "It from bit," by which he meant that the things of the world, the its, might at bottom arise from acts of information, from yes and no answers to questions put to nature, from bits. Existence itself, he suspected, might be made not of stuff, but of answered questions, of observations registered. It must be set down with the same firmness as before that this participatory vision is Wheeler's interpretation, his philosophical conviction, and not an established result of physics. Many physicists regard it as a beautiful overreach, a poet's leap beyond what the experiments warrant. The delayed choice results, they would say, are fully explained without any need for a participatory universe, by the careful understanding that quantum histories are not definite until an experiment is complete. The Decoherence account, in particular, would say that the universe became definite not because observers looked at it, but because its parts have been ceaselessly entangling with one another since the beginning, measuring one another without any mind present at all. Wheeler's vision is one possible reading of the strangeness offered by one of its deepest students, and it has the value of pressing the question to its limit. But it is a reading, not a finding, and the honest mind holds it as such, admiring its reach without mistaking it for proof. Still, even stripped of its boldest claims, Wheeler's cosmic experiment leaves behind an image that lingers in the dark. Starlight that set out before the Earth was formed, crossing the long emptiness for an age, carrying its undecided wave of possibility, intact across distances the mind cannot truly hold, and arriving at last at a single small instrument on a single small world, where its long journey is, in some sense, completed only at the moment it is finally received. The light waits, in a manner of speaking, through all those eons, for the act of arrival that will turn its crossing into a fact. There is something in that image that touches the original question from a new direction. If observation has any role at all in the settling of the world, then that role is not confined to the laboratory. It reaches out to the stars. The oldest light in the sky is light that has been, in its own quiet way, waiting to be met. That reaching outward from the bench to the stars leads to a question that gathers up everything this night has touched and turns it toward the cosmos as a whole. If observation, or measurement, or interaction has some role in turning possibility into fact, then what of the universe itself? The universe is the one system that has nothing outside it. There is no detector beyond its edge, no apparatus standing apart from it, no external observer who could measure it and collapse its possibilities into definiteness. Every observer is inside it, made of its matter, bound by its laws. If a measurement requires something outside the measured system to do the measuring, then the universe as a whole can never be measured, for there is nothing outside it. And yet the universe is manifestly definite. The galaxies hang in their places. The light arrives. The past is, for the most part, fixed and recorded in rock and in starlight. How did the one system with no outside become definite, if definiteness requires an outside? This question is not a parlor game. It sits at the foundation of the science called quantum cosmology, the attempt to apply quantum mechanics to the universe as a whole, to its very beginning, when everything that now exists was compressed into a region smaller than an atom, and the quantum rules would have governed all of it. To speak of the wave of possibility for the entire universe, the wave function of the universe, is to confront the measurement problem in its starkest form. There can be no external observer to collapse that wave. Whatever made the early universe settle into a particular arrangement, it could not have been a watcher standing outside, for there was no outside and no watcher. And this is one of the reasons that some cosmologists have been drawn toward the interpretations that need no external observer at all, toward the many worlds picture in which nothing collapses and the universal wave simply branches, or toward the decoherence picture in which the parts of the universe measure one another from within. No outside required. For the cosmos as a whole, the idea that observation by a mind brings reality into being is not merely doubtful. It is impossible, unless one is willing to believe that the entire history of the universe hung in undecided suspension until the first creature opened the first eye, billions of years after the galaxies had already formed. The geology, the fossil record, and the ancient light all testify against it. The universe was definite long before anyone was present to see that it was. And so the more careful and more beautiful answer, the one that flows from the account of decoherence, is that the universe has been observing itself, in the only sense that matters physically, since its earliest moments. Every particle that interacted with another, every photon that scattered, every clump of matter that pulled on its neighbor was a measurement of a kind, an entanglement, a tying of one part of the world to another, a scattering of possibility into the irrecoverable record of the whole. The universe needs no external observer because its own ceaseless internal interaction does the work. It measures itself everywhere, at every instant, and out of that endless self-measurement, the definite world precipitates. There is no watcher at the edge of creation. There is only the world touching itself and becoming real in the touching. Nowhere is this idea more concrete or more astonishing than in the modern account of how the largest structures in the universe came to be. For the great arrangement of the cosmos, the galaxies gathered into clusters. The clusters strung along vast filaments with immense dark voids between them. The whole sprawling architecture of light across billions of light years traces its origin, according to the leading cosmological theory, to quantum uncertainty. The grandest things that exist grew from the smallest possible flickers of indecision in the wave of possibility. Flickers that were, in the language of this night, observed into definiteness by the universe itself. The theory is called cosmic inflation, proposed in its first form by the physicist Alan Guth in the year 1980, and developed by Andre Linde and others in the years that followed. It holds that in the first unimaginably brief sliver of time after the beginning, very much less than a single second, the universe underwent a stupendous and accelerating expansion, swelling by an enormous factor in an instant, stretching a region far smaller than a single particle to a size larger than everything we can now see. And during that swelling, the quantum fields that filled space could not have been perfectly smooth. The uncertainty principle forbids it. Just as a particle cannot have a perfectly definite position and motion at once, a field cannot lie perfectly flat and still everywhere. It must shimmer, must flicker with tiny quantum fluctuations, faint ripples of possibility appearing and vanishing across the smallest scales. The unavoidable restlessness of the quantum world that allows nothing to be perfectly at rest. These fluctuations were, at first, smaller than atoms, fleeting and microscopic. The kind of quantum trembling that ordinarily comes and goes without leaving a trace. But the inflation seized these tiny quantum ripples and stretched them. As space swelled outward at its tremendous rate, the microscopic fluctuations were carried along and enlarged, blown up from subatomic flickers to scales spanning the cosmos, frozen in place as the expansion outran their ability to fade. What had been the faintest quantum uncertainty became, by the end of inflation, a pattern of slight variations in the density of matter and energy spread across the whole young universe, regions very slightly denser and regions very slightly less dense. The difference is minute, no more than a few parts in 100,000, but real, and now imprinted on the largest scales. The quantum trembling had been written across the sky. And then, crucially for this night's question, those stretched quantum fluctuations had to become classical. They had to stop being a superposition of possibilities and become a definite pattern of actual densities, a particular arrangement that could go on to shape the matter of the cosmos. This is the same transition that has run through everything tonight. The passage from quantum spread to classical fact, and in the early universe, it is thought to have happened through decoherence, through the ceaseless interaction of the fields and particles of the young cosmos entangling with one another, scattering the coherence of the fluctuations, fixing them into a single definite distribution. The universe, with no observer outside it, observed its own first uncertainties into permanence. The quantum became classical not because a mind looked, but because the world, interacting with itself, could not help but record what it had become. Some of the precise details of how this decoherence unfolds in the early universe remain a subject of active research and honest debate. For the conditions of that era are extreme and difficult to model. But the broad picture, that the structure of the cosmos descends from quantum fluctuations made classical, is supported by a remarkable convergence of theory and observation. That observation comes, most powerfully, from the oldest light in existence, the cosmic microwave background. For the first several 100,000 years after the beginning, the universe was too hot and too dense for light to travel freely. It was a glowing fog, an opaque plasma in which light was scattered endlessly and could not move in straight lines. Then, about 380,000 years after the beginning, the universe had expanded and cooled enough for the fog to clear, for the swirling particles to settle into stable atoms. And in that moment, the light was suddenly set free to travel. It has been traveling ever since, for nearly 14 billion years, stretched and cooled by the expansion of space, until it is now a faint whisper of microwaves filling all of the sky. A glow at a temperature of just under 3 degrees above the coldest possible cold. This is the cosmic microwave background, the afterglow of creation, the most ancient light that any instrument can ever detect. And within it is written the pattern of those early density variations, the very fluctuations that began as quantum uncertainty and were stretched by inflation and made classical by the universe's measurement of itself. When the most sensitive instruments map this ancient light across the whole sky, they find it almost perfectly smooth, the same temperature in every direction to extraordinary precision. But not quite. There are tiny variations, spots very slightly warmer and spots very slightly cooler, differences of only a few parts in 100,000, the faintest modeling on an almost uniform glow. And those tiny variations are the fossils of the early fluctuations. The slightly denser regions, where matter was very slightly more concentrated, show as slightly different in the ancient light. And those slightly denser regions, over the hundreds of millions of years that followed, pulled in more matter by their gravity, growing denser still, gathering gas and dust until the first stars kindled within them, and then the first galaxies, and then the clusters and the great filaments, until the universe arrived at the structure we see today. Every galaxy, every star, every world, every grain of every living thing, gathered around the seeds of those original variations. And those variations were, at their root, quantum fluctuations, flickers of uncertainty in a field, made permanent by the universe observing itself into definiteness in its first moments. It is worth resting in this for a while, quietly, because it joins the smallest and the largest things in a single thread. The pattern of galaxies across billions of light years is the pattern of quantum uncertainty, enlarged. The architecture of the cosmos is the shape of the early universe's indecision, frozen into fact. The question that runs through the double slit, the question of how a spread of quantum possibility becomes a single definite outcome, is the same question that governs why the sky is filled with galaxies rather than perfectly empty and smooth. Had the early fluctuations never become classical, had the universe never measured itself, there would have been no seeds for gravity to gather, no clumps to grow into stars, no structure at all, only an endless featureless thinning of gas, cooling forever in a perfectly smooth and lifeless dark. The fact that anything exists in particular, that there are places and things, and besides, rather than a uniform nothing, may rest upon the transition from quantum possibility to classical fact, carried out by the universe upon itself, before there was anyone to witness it. This is perhaps the deepest place to which the question of observation leads, and it is a humbling one. The act of measurement, the becoming definite, which began this night as a curiosity about electrons and slits, turns out to stand at the foundation of the visible cosmos. Whatever observation truly is, whatever happens when possibility settles into fact, it is not a marginal feature of the world, not a quirk confined to laboratories. It is woven into the origin of structure itself, into the reason there are stars to look at and eyes to look with. The universe became a place of definite things, and only because it did so are there observers within it now, gazing back at the ancient light, reading in its faint modeling the record of their own beginning. The watchers are made of the structure that grew from the fluctuations that the universe long ago observed into being. In some quiet and circular way, the observers are the children of the first observation. It is time then to return to the words that opened this night and to weigh them honestly. Observation might be a physical force. After everything, what can be said of that suggestion? The honest answer is layered, and the layers matter. In the strict and technical sense that physics gives to the word force, the answer is no. Physics recognizes 4 fundamental forces, 4 basic ways that the things of the world push and pull upon one another. There is gravity, the gentle universal attraction that holds the planets to the sun and gathers the galaxies and bends the path of light. There is electromagnetism, the force that binds atoms into matter and carries light across space, and lets a hand rest upon a table without passing through it. There is the strong nuclear force, which holds together the cores of atoms against the mutual repulsion of their tightly packed parts. And there is the weak nuclear force, which governs certain slow transformations of particles and lights the first fires of the stars. These 4, so far as the most exhaustive searching has ever found, are the only fundamental forces in nature. Observation is not among them. There is no 5th force of looking, no field of attention, no measured push that the act of finding out exerts upon the world. In this precise sense, observation is not a force, and anyone who claims that science has discovered the mind to be a physical power reaching into matter has gone beyond what is known, into a country that the evidence does not support. And yet the act of measurement does something, and the something is real, and it is nothing. The frozen atom is real. The vanishing stripes are real. The settling of possibility into fact is real, and it is the central, unexplained event of the most precise theory ever devised. So the suggestion that observation might be a physical force is best understood not as a claim that science has confirmed, but as a doorway into the genuine mystery that science has uncovered and not yet solved. Measurement is not one of the 4 forces, but measurement is the place where the smooth equation breaks off and the recipe begins, the place where the theory stops describing and starts prescribing. Whatever measurement is, it is not described by any known force, and it is not described by the equation either. It stands, still, outside the closed circle of what physics can derive. It is named, used, and confirmed in its predictions, and not understood. To say that observation might be a force is to point at that gap, at the unexplained transition, and to wonder whether someday it will be filled by something we will recognize as a process in the world, perhaps a real collapse, perhaps the branching of worlds, perhaps something not yet imagined. What the careful study of the matter does establish, beyond the reach of interpretation, is that the old picture of observation as a pure and weightless witnessing is false at the finest grain of things. The guest who took nothing and left no mark was always an idealization, true enough in the world of fields and windows where the exchanges are too faint to count, but untrue at the scale of single particles, where to look is to touch, and to touch is to alter. At that scale, finding out has a cost always, though the cost can be made very small by looking gently. Information and disturbance are bound together. To learn is to interact, and to interact is to change. This much is settled. The witness was always also a participant, however slightly, and only the vastness and warmth of the everyday world hid the participation from view. But the deeper claim, the claim that observation is the active hinge on which reality turns, that the act of measurement is what calls definiteness out of possibility, this remains unproven and contested, held in different forms by the different rooms of the great house. In the many worlds room, there is no hinge, because nothing is ever called out. Everything simply continues. In the pilot wave room, there is no hinge, because everything was definite all along. In the objective collapse room, the hinge is real, but it has nothing to do with observation, turning instead on the number or on gravity, depending on whether or not anyone watches. In the Copenhagen room, the hinge is real, and it is measurement, but what measurement is goes undefined. In the relational room and the room of quantum belief, the hinge is reframed as something about relationships or about information, not a force in the world, but a feature of how systems become real to one another, or how minds update their expectations. The honest state of the question is that we do not know whether observation is the active maker of facts, or merely the passive bookkeeper of facts made by other means. The experiments do not say. They have never said. They predict the results with perfect fidelity and remain silent about the story beneath. There is a particular kind of peace in that silence, if one can learn to rest in it rather than fight it. The peace of an open question held without anxiety, turned slowly in the dark, neither forced to a conclusion nor abandoned in frustration. The greatest minds who have studied this have not resolved it. Bohr did not resolve it, nor Einstein, who never accepted the strangeness and spent his later years convinced that something essential was missing from the theory, that the wave of possibility could not be the final word, that, as he put it, the deeper reality must be more definite than the equation allowed. Wheeler did not resolve it for all his daring. The argument runs on, civil and deep, among living physicists today, in the journals and the lecture halls, with no end in sight and no shame in the lack of one. Some questions are not failures for remaining open. They are the marks of a frontier honestly reached, the places where understanding has pressed as far as it can and met something that does not yet yield. The measurement problem is such a place. It is the edge of what is known, and it has been the edge for 100 years, and there is a strange comfort in standing at an edge that so many careful travelers have reached before and found, as we find, that the path simply waits there in the dark for someone yet to come. What remains, when the arguments are set down for the night, is not an answer but a changed sense of the world. The universe is no longer quite the finished machine, turning indifferent in the dark, that the old picture described. It is something more intimate and more strange, a world in which the smallest things do not hold definite values until they are drawn into relation with other things, a world that becomes definite through interaction, that measures itself into existence through the endless mutual touching of its parts. The grass in the field does not wait for the watcher at the window, but it does not stand wholly alone either. It is held in being by the sunlight that falls on it, and the air that moves through it, and the warmth of the ground beneath. All of them, in the language this night has learned, observing it, fixing it, drawing it out of the haze of what it might be into the certainty of what it is. Definiteness is not a given. It is an achievement, carried out everywhere, constantly, by the world upon itself, and the solid, familiar shape of things is the result of that ceaseless, quiet labor, never resting, never finished, going on in every grain of matter through every instant of time. And the watcher at the window, the human observer who began as the innocent guest of the visible world, turns out to be woven into that labor too, not as a special power, not as a mind that commands the atoms, but as one more part of the universe doing what every part does, interacting, entangling, becoming definite in relation to everything else. And in that becoming, somehow, growing aware, the observer is not outside the world, reaching in. The observer is the world, looking back at itself, made of the same fluctuations that the early cosmos observed into being, gazing now at the ancient light that carries the record of that first settling. The circle closes softly. The universe became definite, and in its definite places stars formed, and around the stars worlds gathered, and on at least one world the gathered matter grew complex enough to look up, and to ask how the looking and the looked at could be so strangely bound, and to find, at the bottom of the asking, only more questions, and the long silence between the stars. So the night settles toward its close, and the question can be allowed to slow and soften and spread out the way the ancient light spreads thin across the sky. There is no need to hold it tightly any longer. It will keep. It has kept for 100 years, and it will keep through this night and many nights after, waiting in the patient way that deep questions wait, asking nothing, refusing nothing, simply present, like the faint glow that fills all of space and asks only to be received. Return one last time to the atom in the trap, the small thing held still by being watched, the image that opened all of this. There is something in it that gathers up the whole of the night, a single atom prepared in one state, ready to change, ready to slip quietly into what it would become if only it were left alone. And the gentle, relentless attention that holds it back, that resets its small clock again and again, that keeps the future from arriving so long as the watching continues. It is not a violent thing. There is no force in the ordinary sense, no push, no grip. There is only the steady asking of a question, "What are you now? What are you now?" and the atom answering each time, "Still here, still as I was," and in the answering remaining. To be watched, in that strange corner of the world, is to be held in the present, kept from departure, suspended in the moment one occupies, unable to drift away into the next thing so long as the eye does not waver. There is a kind of stillness in it that the mind can almost rest inside, a held breath that need not be released, a present moment that does not have to end. And perhaps that is the truest thing this long inquiry leaves behind, not a conclusion about forces, not a verdict among the rooms of the great house, but an altered feeling for the act of attention itself. To observe is nothing. Whatever it finally turns out to be, in the deep accounting of physics, it is not the weightless and uninvolved witnessing that it once seemed. The looker and the looked at are bound together, at the finest grain of the world, in ways that the old picture never allowed. The boundary between them is softer than it appears. And the universe, far from being indifferent to whether it is observed, is built throughout from acts that resemble observation, from the mutual measuring of its parts, from the endless quiet labor by which possibility is drawn into fact. The cosmos does not merely permit watchers. In some sense, it is made of watching, of interaction, of one thing becoming definite in relation to another, all the way down to the first fluctuations, and all the way out to the farthest galaxies whose light is only now arriving. The galaxies turn, slowly in the dark, each one a wheel of 100 billion stars, drifting through a space so vast that the light between them takes ages to cross. They formed around the seeds of an ancient indecision, quantum flickers stretched and frozen, and observed into permanence before the first dawn. They will go on turning long after this night, long after every night that anyone will ever know, cooling and reddening, and slowly winding down across spans of time, beside which a human life is less than the blink of an instant. And the light they shed travels outward in every direction, crossing the emptiness, carrying its undecided wave of possibility across the long dark, waiting, in its own quiet way, to be met. Somewhere, perhaps, it will fall at last upon an instrument or an eye, and in that meeting, its long journey will complete itself. And what was a spread of possibility crossing the void will become a single registered fact, a point of light, an answer to a question that the cosmos seems always, gently, to be asking of itself. There is the silence between the stars, deeper than any silence that can be heard, the silence of distances too great for sound or signal, the silence in which the galaxies drift without ever touching. There is the dark, the immense and patient dark that fills almost all of space, against which the few scattered fires of the stars seem small and precious and brief. There is the slow turning, the wheeling of the great spirals, the orbiting of the worlds, the long, unhurried motions that take ages to complete and care nothing for haste. And there is the long time, the deep time, the vast reaches of years across which the universe became definite and gathered itself into structure and kindled its stars, and at last, on one small world, opened a single watching eye, all of it held in the same quiet question. What does it mean to observe? What happens when the possible becomes the actual? And how is it that the watcher and the watched, the eye and the ancient light, the small attention and the vast indifferent cosmos, turn out to be, in the end, made of the same stuff, bound by the same strange thread, two faces of a single slow becoming? The question does not need an answer tonight. It has waited 100 years and will wait gladly through the dark hours ahead. Let it drift now, the way the light drifts, the way the galaxies drift, unhurried, unconcluded, at peace with its own openness. The atom in the trap is still being watched somewhere, still held in its present, still answering, still here, still here. The ancient light is still arriving, still completing its long crossing in the meeting with the eye, and the universe goes on observing itself into being, everywhere, in every instant, without urgency, without end, drawing the definite world out of the haze of all it might have been, quietly, patiently, in the dark, in the silence, in the slow and certain turning of the deep. If these long passages through the quiet places of the cosmos bring some measure of stillness, and a way to drift toward sleep beneath the deep time and the far light, you are warmly welcome to subscribe and to leave a gentle sign that you were here, so that more of these slow nights among the stars can find their way to you. Rest well. The galaxies will keep turning while you sleep, and the ancient light will keep arriving, and there is nothing tonight that needs deciding. Let it all drift. Let it all settle. Let the long dark hold you softly until morning.